It's really a pleasure to join this conference. So I will talk about the prospect and the progress of the Jinping Neutrino Experiment. In this talk, I will basically cover these aspects, the motivation, and a brief introduction for the Jinping Laboratory. Also tell you about the Jinping Neutrino Experiment proposal and all the R&D effort which are being carried on. Some more wild idea about measuring the potassium, 40, and mantle geo-neutrinos. So this is the outline. We have strong interest in the solar, supernova, and the geo-neutrinos. So for the sun, we know it's fielded by the PP fusion chain and CNO fusion cycles. Particularly this CNO cycle is really minor, 1% in the sun. However, it's 99, dominant in the other high mass stars. Then the energy is propagated to the surface. In the inner core, it's through radiation. There's a parameter called radiation opacity govern the propagation of the energy. And the outer layer is through convection. Then this whole system relies on a balance of gravity and the pressure given by radiation and particle pressure. This model is a dynamic model. It's not a static picture, so it requires a lot of boundary conditions to make this model run. For example, it requires the abundance of hydrogen, helium, and other metal elements. Also rely on the current, radius, age, mass of the sun. Also, there's a strong assumption. It is the if this is a model, it's really you need the initial metal fractions. So the current assumption is use the surface fraction, and it is same as the core fraction. It's also the same as the initial fraction. So this is the diagram for PP chain and the CNO cycle. This is where the neutrino are emitted. Beyond the interest in seeing CNO, since it's the major fueling interaction for high mass stars, so there now has a new conflict. It's between the new measured helioseismology result and sound speed. So we have a new, basically, to the better calculation of the solar model. It has a new input and the 3D calculation, etc. So it predicts the sound speed differ by the previous calculation by 40%. So here we have a simple diagram. It tells, okay, we have all these primordial heavy element fractions as input. So for the CNO neutrinos, there really has a direct dependence between each other. However, for the other neutrino component, they are mainly governed by the radial opacity through pressure, density, temperature, etc. So this can also then gives the sound profile. So there's a degeneracy between the solar metallicity problem and the radial opacity. So CNO neutrinos really stand for a direct probe for this question. Certainly, we also have the interest in the solar neutrino oscillation. So this simple cartoon really shows the feature in this solar core in the neutrino generated. They are mainly electron neutrinos. However, through this irregular oscillation pattern include the matter effect, so it's reach this balanced status at the surface of the sun. So there's a upturn feature, so-called upturn feature in the solar electron neutrino oscillation. So these are some basic questions we are interested in. For example, the CNO neutrinos, want to see how discover this, and it's a direct probe for the solar core. Also want to measure the neutrino oscillations of the sun. The second motivation is geo-neutrinos. So it's still there's a lot of energy of our Earth. So for example, the Himalaya mountain area is still moving towards the northeast direction in this speed, 0.5 centimeter every year. So every year we have this measurement is still moving on. The energy can be the initial gravity. Also, there's another possibility is nuclear power from uranium, thorium, potassium decay. This is our current knowledge from global heat measurement and theoretical prediction, also the geo-neutrino measurement from Kamlan, Brachino, etc. So the short conclusion, we are still consuming initial gravitational power, and we want to, certainly there are also contributions from all these heat generation elements. So we want more measurement to have more understanding about geo-neutrinos. The other topic is the supernova relic neutrinos. So here I basically, okay, this is the supernova relic neutrino spectrum. I lay out a simple formula, just indicate why its importance. So here it requires the input of the core collapse supernova rate. Also the neutrino energy spectrum from the supernova is somehow can be predicted by the given supernova temperature. The other constants are like redshift, etc. So basically supernova red neutrino is a fingerprint of the star formation rate and star evolution mechanism. So I'll give a brief introduction for the Jinping Laboratory. So this is a map, China and other neighbor areas. So this is where the Jinping is. If people are more familiar with Juno experiment here, so they are still 2,000 kilometers away from each other. This is in the mountain area. We have a river band. We have a tunnel connecting all these rivers. So it's basically easy to reach. There are direct flights from Beijing, all the major cities, Shanghai, Guangzhou, etc. We can fly this to airport, then take a car. It's about 2 hours drive. So comparing to the other famous underground lab in the world, so it's reasonably good. So it's famous by its overburden, 2,400 meters of rock. Then it's the deepest underground lab. So if we're talking about muon and the other muon-induced background, it's 200 times, 200 times less than ground social, and half of the snow laboratory. Beyond the overburden, it's also far away from all the commercial reactors. So this is where the Jinping lab is. So all these red are the Chinese nuclear reactors. So the closest reactor is 1,200 kilometers. So then it is an ideal site for low background neutrino experiment, has the lowest muon flux, also has the lowest reactor neutrino rate. This is what the phase 1 of this laboratory looks like. It's only a small laboratory. Currently, it's hosting 2 dark matter experiments. One is called CDAX using germanium detector. The other one, PandaX, use liquid xenon. There are also some low background for these facilities. Now, in this access tunnel, we have a one-time prototype for this neutrino program. That's phase 1. Then this is phase 2 layout. So this is the volume rock work. And for phase 2, for the laboratory space, it's expanded to this number, 100 or 0.1 million cubic meters. You also have the power and the fresh air planted. Another nice feature is, since this is a water hydropower plant, there are several underground tunnels. They are running waters to generating power. So it has direct access to cool water. It's for all the year. It's like 15 degrees. So it's very easy to access. So this is the status of this laboratory. So this is a laser scan of the finished result taken at May of last year. So all these 4 laboratories done. Each of them is 40 meters wide and 120 meters long. So at the far end, you can see a car parked inside. So it's a huge, huge laboratory. Then there are 2 foundation pits for CDAX experiment and PandaX experiment. They are all finished. This is a plot from, I think, last month. We have the air ventilation system installed. So I think they'll start working in this October. Then a little bit about Jinping Neutrino Experiment proposal. We hope to build a 2 kiloton physical mass for solar neutrino physics. Equivalently, it is like a 3 kiloton for geo and supernova neutrinos. So with this detector, we think we have the sensitivity to discover the CNNP neutrinos and pin down the solar new oscillation, have a precise geo-neutrino flux measurement in the uranium-thorium ratio, and study the supernova relic neutrinos. So this is a sensitivity study for the solar neutrinos. We basically use a lot of information, our experience from Proxino, also taking the overburden of Jinping as input. So this is the famous carbon-11 background. At Jinping, it really can be surprised by a factor of 200. Then bismuth 210 is still the same, assume the same external gamma background, etc. So with increased target volume and high overburden, the O15 neutrino can be reached 10%. Also in this area, we can exactly constrain the uptime oscillation. For the geo-neutrinos, since they're far away from commercial reactors, it has very few background, really have a very clear geo-neutrino signal for thorium and uranium and their combinations. So we can have a clear measurement of the uranium and the thorium neutrino spectrum, and their ratio can be measured to a precision of 10%. We can also pin down if there is any geo-reactors down the car or anything. We can, with this precision, we can address the mantle contributions, etc. So these physics can really be done with the current mature technique, for example, liquid scintillator. But on the other hand, we are also paying some new technology, called slow liquid scintillator. I'll explain this later. With this technique, we can have a better sensitivity for the supernova relic neutrinos. So this figure gives the sensitivity level versus exposure, basically kiloton times year. So this curve, the first curve is basically for the slow liquid scintillator. With a 15 kiloton year detector, we can make a discovery with this slow liquid scintillator. Here, I also have the comparison with GD water, and normal liquid scintillator. Here, I have to apologize. The waveform discrimination method in the LS is not included here. So it should be much better than this plot. Okay, so I will explain some, give some introduction of the R&D effort. So the first one is about this slow liquid scintillator. We have some setup like this. We set up several layers, 4 layers of plastic scintillator to form a cosmic muon telescope. We have a black container here, filled this with liquid scintillator samples. We have a PMT on the top and 1 PMT on the bottom. So 1 PMT is really at the back of the direction of Cherenkov, and the other one really facing the Cherenkov light direction. So then we can look at the waveform detected by those 2 PMTs. For the top PMT, we can see only scintillation light, this blue curve. At the bottom, it's Cherenkov plus scintillation. So this sample is the result from the pure LAB. So this is one of the famous solvent for liquid scintillator. However, this light yield for LAB itself is very low, so not enough for solar neutrinos. So we did more studies for the light time constant and light yield scan by adding PPO and BCNV. So this is the waveform for the top PMT for several samples, several typical samples, and this is the result for the bottom PMT for several typical samples. You can see there is a one-to-one correspondence. For example, this curve corresponding to this curve here. So here there is no prompt peak, but for this sample, for the other PMT, it has a prompt peak at the beginning. So that's the Cherenkov light. So this curve, all these dots can really form a curve. This tells what's the possible combination of decay time constant and the light yield for these type of combination, means LAB plus PPO plus BCNV. So you can distinguish Cherenkov light and the scintillation light has a reasonable light yield. Then here is a rough calculation. So I pick one of the sample in the previous slide, for example, 3,400 photons per MeV for one estimation. We can realize some PMT photocathode 100% coverage, quantum efficiency 30%, and 60% for attenuation. Then we can reach like 612 PE per MeV. So this will be good both for solar, geo, and supernova detections. So on the top is one example we done with simulation of LAB with the real experimental input. Here we can really see the band from electron and the gamma. Okay, the XY axis the number of scintillation photons and the twinkle photons. So electron and the gamma, they have a lot of twinkle photons, but for muon and proton, it's really easy to identify because they don't have twinkle light. So with this combination, we think we can do the directionality about 5 MeV and have this feature of particle identification. Previously, I just mentioned we can realize the PMT photocathode coverage to 100%. So this is how it achieved. So we designed a new light concentrator because of this need of high light yield. So we consider the 3D geometry profile of PMT. So it's not a flat panel, it's a sphere. So with one improvement, this figure shows the efficiency where the red and orange shows the photon finally will hit the PMT photocathode, while the blue and the yellow will be reflected out. So this is basically the efficiency plot over the input aperture. So with this improvement, we can improve the efficiency for some area. We can also use hexagonal openings to fill the gaps. So this will give us something like 100%. So basically, this is the efficiency scan for all cutoff angles for light concentrators. So for example, for 90 degrees, they can really reach like 97, 98%. Certainly, the number of PMT required is a little higher, but still better than without it. So all these tests are done with a small detector, 20 liter, also simulation. Now we are doing making a bigger experiment. It's a 1 ton prototype at Jinping. So plan to measure the underground fast neutron background, test the detection material, for example, water, liquid sinter, or slow liquid sinter. It can also be served as a low background facility and study reconstruction, etc. So it has 30 PMTs, 38-inch PMTs. We use flash ADC to read out. It's a 10-bit, 1 gigahertz sample per second. So with acrylic vessel and the liquid sinter, the 1 ton, outside the water, we have whole detector, we have light shielding. So this is the construction. So it's complete. Now it's sitting in the phase 1 of the CJPL lab. Now it's taking data with one type of the slow liquid scintillator. We already run it for over 100 days. We have now the PMT gain is calibrated and sighted more uniform, and the PMT dark noise has settled down to 5K to 10K hertz level. So we are doing studies about underground background in the slow liquid scintillator. At the same time, we have a comprehensive simulation for detector simulation, flexible for different geometry setup, waveform simulation. We also have a flow style simulation. So it's really different than the John 4 event by event style. So we have new studies for stainless steel, since it's a low background detector. Now we have studied one type of stainless steel analyzed by the GDMS and some germanium detector at Jinping Laboratory. So we found one stainless steel 313L really comparable to the level reached by Broxino in the next experiment. At the end, I'm going to say something about some more wild thoughts about using this slow liquid scintillator. About versatile element on Earth. So we have many elements. So some elements are refractory. That means they are easy to be lustrophile elements, so easy to be attached to rock, etc., like uranium, thorium. But there's another group of elements. They are versatile, like potassium. They are not easy to be stay. We have measured uranium thorium geo-neutrino. They can fix the refractory element. However, we still need measurement for the potassium-40 geo-neutrino to finish this picture for the first element. So then how can we do this? One thought is measure the geo-neutrinos with electron scattering, because we know it's very hard to extract the direction information from inverse beta decay process. Sorry. So the idea is very simple. We have solar neutrinos. However, solar neutrinos are always coming from one direction, but the geo-neutrinos can come from all the other directions. And the scattered electron from neutrino electron scattering have a very good direction correlation to the initial directions. So this is a simulation with an ideal detector with a cut of the kinetic energy, selected kinetic energy for electron above the, missed the unit, 0.8 MeV. We can clearly see solar neutrinos, cross neutrino, and the mantle neutrino. They grouped it in a different region. So with a simple statistical calculation in a 2 kiloton detector with this cut, with a different cosine solar angle cut, for the potassium-40, we can get overall about 50 to 100 candidate. For the mantle, we can have 30 to 46. So quite good statistic, but it's difficult. So how to distinguish the potassium-40 neutrinos beyond this solar angle cut? The potassium-40 neutrinos has a distinguishable structure. This basically comes from the decay structure. So one word is, for example, with one of the advanced detector called LAPPT, it has a timing precision about picosecond. I think this works without any questions. If we want to use PMT, then we probably still have some work to do, or we want to investigate more recipes for slow liquid scintillator. Then this plot shows the projection on the cosine theta Earth. Then we can see where is the cross neutrinos, where is the mantle neutrinos. So usually for current measurement, we have to rely on a lot of geology surveys, maybe 50 kilometers square around the experimental site. But if we can have this information, we can directly use one detector to do this thing. So the next step for the Jinping Neutrino Experiment. So the laboratory has been listed in the 13th five-year national plan for the major science and technology infrastructure program. We also have a good support from the International Advisory Committee for the CGPL. This year in 2015, we have 2 international workshops for all the people who are interested with this experiment. Then this is our current schedule. We are kind of here. So in this year and next year, we are working on a 10-ton prototype. Sorry, we borrowed a figure of CTF. So continue to study slow liquid scintillator and investigate about the low background technique. So here is basically the conclusion. So we have the interest on solar, geo, supernova, relic neutrinos, and the site is ideal for this low background neutrino experiment. Many R&D effort, for example, the slow liquid scintillator. We have some wild thought on the geo-neutrinos, and the 10-ton prototype is in plan. So thank you for your attention.